Section 4.5 is linearization. So let's take a look. This is the definition from the book. Go ahead and copy this down and then come on back and we'll talk about it. So if a function f is differentiable at x equals a, then the equation of the tangent line, written in this form, I'll talk about that in a second, defines the linearization of f at a. So what we're talking about here is if we have a function that is differentiable at a point a, if I draw a line tangent to the curve at that point, then that line is going to be a pretty good approximation for the function value near the point of linearity. Let me draw a little better picture because that one's hard to see the difference. So let's say I pick this point and I do a tangent line. Whoops. So as long as I am close to the point of tangency, the line is a pretty good approximation. The further away I get, the bigger a difference there is between the actual function value and the line value. Excuse me, I've got a bad throat today. So let's take a look at this equation. We're used to having a function written y minus y sub 1 equals m times x minus x sub 1. And actually, the equation up there is the exact same equation, just written in function form. So if I add the y sub 1 to both sides and put it in the front, and I'm doing this at the point where f equals a, so that's the point a comma f of a, we know that the slope is f prime at a. So if I substitute in y equals the y sub 1 value, f of a, plus the slope, f prime of a, times x minus my x value, a. And you can see that this equation is the same as this, where we've used the point a comma f of a and the slope f prime of a. And we call it L of x, which is approximately equal to f of x, excuse me, as long as we are close to x equals a. All right, let's do one of these and see what we can do. Find the linearization of f of x equals cosine of x at x equals pi over 2, and use it to approximate the cosine of 1.75 without a calculator. Now, 1.75 is pretty close to pi over 2, but it's not exact. So let's see what we need to do. Here's here's my function, and here's the point pi over 2. So I want an equation of the tangent line at pi over 2. Now they've already written down what it is here, but let me go ahead and show you how to find it. So at pi over 2, we can find a function value by finding the cosine of pi over 2, which is 0. So my point of tangency is pi over 2 comma 0. To find the slope at pi over 2, I need f prime of x, which would be negative sine x. Calculating f prime at pi over 2, I have negative sine of pi over 2, which is negative 1. So I now have a point and a slope, and I'm going to use that to write an equation of a line that I'm going to call L of x, and that is going to be equal to my y value plus the slope times x minus my a value. Cleaning this up just a little bit, L of x equals 0. Oops, I don't need to write the 0. That's what I was trying to do, clean it up. Equals negative 1 times x minus pi over 2, or we could just say negative x plus pi over 2. So that's the equation of the line tangent to this graph at the point of tangency. I can use this equation to approximate any function value as long as I stay relatively close to pi over 2. So I'm going to go to another screen. So the equation again that I'm using is L of x equals negative x plus pi over 2. And I want to find L of 1.75. So negative 1.75 plus pi over 2 is my answer. That's just a number. Let's do a check on this. My reason for doing this was to find an approximate value for the function where f of x equals cos of x. So if I did f of 1.75, which is the cos of 1.75, and check that in a calculator, I would get negative 0.178246. This value is very, very close to that. As a matter of fact, if I put that in my calculator, I would get negative 0.1792036. So this value is a really good approximation for the cos of 1.75. So f of x is approximately equal to L of x for any value close to the x value that I choose. So that's linearization. We're going to do one other example, which is using linearization to approximate a root. So the root function would be f of x equals the square root of x. And I want to find that at 123. Well, 123 is pretty close to 121. So I'm going to use f of 121, which is 11, as my ordered pair. So when x is 121, f of x, or y, is 11. So that's my point. I need a slope at this same position. So f prime of x is 1/2 x to the negative 1/2, or 1 over 2 root x. So the slope at 121, my point of tangency, is 1 over 2 root 121, which is 1 over 22. So there's my slope, and there's my point at the point of tangency for the square root of 121. I can use that then to approximate the square root of 123 because it is very close. So let's write the equation of our line. L of x equals my y value plus my slope times x minus a, my point of tangency. I'm going to use that to find L of 123. 11 plus 1 over 22, 123 minus 121. So L of 123 is 11 plus 1/11, or 11 and 1/11. So again, this is going to be very close to the square root of 123, and I can do it really easily without a calculator. If you want to check, 11 and 1/11 equals 11.0909 repeating. The square root of 123, if you put that in your calculator, is exactly 11.090536. Okay, so you can see that our approximation done without a calculator, 11 and 1/11, is really close to the actual square root of 123. So that's it for part 1 of section 4.5.